Hello everyone, my name is Mayur Ubale. I am a assistant professor in WIT Solapur. So today we are going to learn about design of coarse bar screens as primary treatment operation in wastewater treatment plant or WWTP. So what are learning outcomes? Students will be able to design a coarse bar screen as primary treatment operation in WWTP. Now, let us have some a brief discussion about what are bar screens. So, screenings serves as the first unit operation within wastewater treatment facility or what we can say wastewater treatment plant. It is a kind of an essential device which is equipped with uniformly sized openings designed to capture whatever coarse suspended particles or floating materials or debris which are present in the incoming wastewater. It can be different type of fragments, wood pieces, then leaves, plastics, even rags, papers, and similar items which are floating in nature. So we have to remove these floating materials. So why do we need to remove? As when these materials come into treatment unit, the chances are they may damage to the downstream equipments which are present in the secondary treatment unit or in the tertiary treatment unit. They can damage valves, they can damage pipelines, they can damage different type of impellers, and ultimately it compromises the overall reliability and efficiency of each treatment unit and overall whole treatment system. So screens becomes much more important while removing these particles. Now, when we are moving ahead with technicality, we must understand that screenings are of three types. The first one is core screens. We can say as bar racks or bar screens, which are having a pore size between 6 to 150 mm. Then comes fine screens, which remove particles lesser than 6 mm. So those particles which are having size greater than 6 mm can be removed in core screens, and if they are lesser than 6 mm, they can remove by fine screens. But I need to remove even lesser particles like 0.5 micrometer. I can go with micro screens. So when I divide the screens, it is core screens, fine screens, and after that micro screens. Now, so while designing the core screenings, we must understand that few parameters are there, and for which we have to assume their range or any value from this range. So first of all, for openings, that is clear openings, that is core screenings, it is having a range value of 6 to 150 mm, which is kind of equivalent to 0.25 to 6 inches. Now, if I am going for bar screen openings, I have to look at the range of 15 to 40 mm. Typically, the value taken as 25. But we have to understand that as these bars are inclined with respect to vertical, so their spacings should be kind of proper for whole wastewater stream. Then when I am looking at rack angle or inclination of bars, generally it is taken as 45 degrees, so that proper effective cleaning should be happening. Then when I am going for mechanically cleaned rack angle, I have to take as vertical, that is 90 degrees Celsius, sorry 90 degrees, making sure that openings must exceed by 25% of channel cross section. Then what should be the velocity through the screen? It is generally in between 0.6 to 1.2 meter per second. Then what should be the minimum velocity by which whatever particles which are present in the wastewater should not settle down? So minimum velocity should be always equal to or greater than 0.3 meter per second. Then the velocity of wastewater which is incoming, or we can say stormwater, is generally taken as 0.8, that is velocity before the screenings. Then what should be the head loss? Just general head loss is considered to be 0.15 meter, but it is for clean screens. And what should be the maximum head loss which is permissible in nature? It should be lesser or equal to 0.3 meters. So basically, what happens with respect to time, the clocks will be there in the pores of the screenings, and slowly velocity will slow down and head loss will increase, by which whole system may get collapse. And for that we have to fix permissible head loss, that is 0.3. Now generally the head loss is having a formula, that is small h is equal to capital V square minus a small v square divided by 2g, where capital V is velocity through the screen and the unit we have to consider as meter per second, and small velocity is velocity before the screenings, again the unit would remain same, that is meter per second, and g is your gravity, where we have to take the value as 9.81 meter per second square. Now we will try to design a bar screen which is mechanically not cleaned. Fine, it can be considered as a coarse screen or a rack angle, but it is hand cleaned. So the question would be, design a bar screen for a peak average flow of 40 million liters per day, that is 40 mld. So for that, first we have to consider various range values, like I am inclining these coarse screens by 45 degrees with vertical, that is the first assumption. Second, I will consider a bars which are having a size of 9 mm by 50 mm, where 9 mm thickness is facing the flow. Fine. So, and 50 mm is kind of parallel to the flow. Then I will consider the clear spacing between these bars to be 36 mm, and the desired velocity through the screenings would be 0.8 meter per second at peak flow. Fine. Now at a maximum flow rate which is given in MLD, I will convert it into meter cube per second, that is 40 into 10 raised to 6, that is million liters, multiplied by 10 raised to minus 3, converting liters to meter cube, divided by 24, that is 24 hours, multiplied by 60, converted into minutes, multiplied by 60, converting it into seconds. So meter cube per second it will be coming, and value would be coming as 0.463 meter cube per second. Now this is the maximum flow rate. Now I have to get what should be the area. As we know, Q is equal to AV, and I know the velocity value, I know the flow rate value. So just by reconsidering, the net area or small a would be equal to Q divided by small v. Fine. So that is 0.463 divided by 0.8, where 0.8 is velocity through the screenings. So value is coming about 0.5787 meter square. As this is a net area, so what should be the gross area, that is of total screens? So 0.5787 multiplied by 45. So from where the 45 is coming? Basically, if I go back, this is the 46, that is clear spacing, and this is a 9 mm which is facing the flow. So 9 plus 36, that is 45. So 45 divided by 36, which is coming about 0.7234 meter square. Fine. Since these are inclined to the horizontal, so I have to divide it by sine 45 degrees. So that is sine theta. Fine. So by calculating, I will get a value about 1.023 meter square. So this is overall gross area of screens. Now when I am looking at a velocity which is before the screens, what I have to do? I have to reduce down the velocity. How I can do it? So that is 0.8 multiplied by clear spacing divided by clear spacing plus size of the bar, that is 45. So 36 divided by 45. I will get the value about 0.64 meter per second. So for the formula of head loss, your capital V, that is velocity through the screening, will be becoming 0.8 meter per second, which you had assumed already. And what is small v, that is velocity before the screen, that is 0.64 meter per second. Just by putting these values into the formula, that is 0.729 in bracket 0.8 whole square minus 0.464 whole square, I will get the value of about 0.017 meters, or I can say 1.7 centimeters. So this will be the head loss when the screenings are kind of clean, or the initial stage of cleaning. But what will happen if suppose we are assuming that screens are half clogged? At that time, your velocity through the screening would be double down. Why? Because your cross section area is half, but your flow rate is same. And when I keep q is equal to av, automatically my velocity should be doubled up. So 2 multiplied by 0.8, which is coming about 1.6 meter per second. Again I will keeping this value into the formula, and I will get the head loss about 0.157 meters or 15.7 centimeters. So this is the head loss when when your screenings are half clogged. So understand, when screenings were fully cleaned, so at that time the head loss was 1.7 centimeters only. But if it is half clogged, it is 15.7 centimeters. So if we try to assess it, what we can say, that it is when the screens are half clogged, it is the head loss is shooting up by 9 times. So just by halving the screening area, your head loss is shooting up at a very faster rate. To stop that, what we have to say, that you have to clean it very frequently. If suppose head loss is not happening at a very faster rate, we can say that yes, you can do at a lesser frequent way. If head loss is shooting up at a very faster rate, you must say it must be cleaned by 2 times or 3 times per day. Fine. So this must be your analysis. So let us have few review questions. The first one is, velocity through bar screenings is always greater than that of velocity before the screenings. True or false? The next MCQ is, hand cleaned screenings generally having an inclination of dash with horizontal surface. And another MCQ is, minimum openings required in the bar screenings are. So this is the value. So what is the correct answer? For the first one, yes, the statement is true. The another one is, for hand cleaned generally we keep it 45 degrees, and for minimum spacing it must be 6 mm. So these are the MCQs and overall design of bar screens, and I have used these references to make this presentation. Thank you very much.